The second part of section 2.3 is about the intermediate value theorem. It's the first example of a theorem in calculus that we're going to use together. And you might notice that that list of math practices for AP Calculus, reasoning with theorems is one of the big jobs we have to prove that we're doing good mathematics this year in calculus. So I think you already know how to do this, we just haven't done it in calculus yet. So I'm going to bring up this example from geometry to kind of remind us that we know how to use theorems and point out some important language that we're going to be using. So I just got this off the internet. This is an example of a theorem. It's called the vertical angles theorem. And that says if two angles are vertical angles, then they have equal measures. So what is a theorem? A theorem is a math theorem is a mathematical statement, a mathematical truth that can be proven. And the thing is that once somebody proves it, and maybe a few other people prove it, and they all get the same result, they all feel like they're confident in their proof, enough people read about it and enough people use it, we all agree to it. We don't feel like we have to reprove it every time we want to try to say whether those two vertical angles are equal. So here, a key part of a theorem contains a hypothesis. A hypothesis is the part typically that comes after the word if. So here the hypothesis is two angles are vertical angles. And the conclusion is the part that comes after the n. They have equal measures. So you probably learned this theorem and your geometry teacher probably made you prove it again, and then after a while you're like, okay, the vertical angles theorem, I know it. And now that you know it and you know that it's been proven by enough other people, you just absorb it into your language, and it can serve as a justification for statements that you make. So you might say then, the next day in class, if somebody says to you, what is the measure of angle MHL? Justify your answer. If they just asked you the measure, you'd say, oh, 129, I know it. If they ask you to justify your answer, you're going to use language from that theorem. So you might say that since angle OHK and angle MHL are vertical angles, therefore they must have equal measure, and I conclude that the measure of angle MHL is equal to 129 degrees. So you had to state the reason that you know it's okay to use the vertical angle theorem, and here that's pretty easy. It's because OHK and MHL are vertical angles. So you have to connect it back to the theorem, connect it back to the hypothesis. Prove to me that you know the hypothesis is true, because we know that if the hypothesis part isn't true, then you can't make any conclusion. So since those two angles are vertical angles, then they must have equal measure. So as we learn our first calculus theorem, notice how we use those words, since and then, that sort of match up with the if and then from the theorem. So this brings us to our first theorem in calculus, the intermediate value theorem. We've just learned about continuity. We've learned that a function is continuous. It has no holes or skips or jumps in it. And we are going to use this intermediate value theorem. It's an application of continuity. So just like first you learned how to solve equations, and then you learned how to use equations to solve problems, here we just learned about continuity. We're going to see what kinds of problems we can solve because of continuity. So the intermediate value theorem is one category of problems we can solve now. So notice, so watch for some of those same words. The intermediate value theorem, there are two different wordings, one on this slide and one in your paper. Pick one, memorize it. If, then. Okay, there's another then. So if a function is continuous, that means no holes, no skips, no jumps. And I know two ordered pairs on that function, a comma f of a and b comma f of b. If there's some y value in between f of a and f of b that for some reason is interesting to me, I can be guaranteed that somewhere in between a and b, my function is going to have to cross. That's because I know the two y values, f of a and f of b, and I know my function has to be continuous, which means there's no y in between the y up here and the y down here that can get skipped. I can't skip. If I'm going to connect these 2 points with a continuous curve, I can't skip over any. So let's see what that looks like. So essentially, the intermediate value theorem says that because a function, well, if a function is continuous, then because it is continuous, it must take on every y value in between two y values that you know. So this k is just a letter we use. There's a place for you on your paper to decide, do you think k is a y value or k is an x value? And then similarly, do you think c is an x value or c is a y value? An input or an output. So imagine this, if k is some y value that I care about, imagine drawing in that horizontal line, y equals k. If I know two ordered pairs, let me get the pen, if I know this ordered pair and this ordered pair, and my y, the k, the y that I care about is somewhere in between them, so here's my dotted line, y equals k, is there any way to connect this point and this point with a continuous curve that doesn't cross f of k? Not f of k, that doesn't cross y equals k? There's no way to do it because you would have to skip over that value, and continuous functions don't have skips. So we just give a name to that place. This is the x-axis, this is the y-axis. We call it c, you can call it anything you want. But there is some x value in between a and b where your curve is going to cross that horizontal line, y equals k, which means the output value here, that whole ordered pair, is going to be c comma k, which implies, of course, f of c equals k. Don't worry, we're going to do lots of examples. So just notice on your notes paper I put a similar picture. I asked you to circle on the graph any ordered pair for which I don't really love what I wrote there. I think it's more clear if I had written f of x equals k. So could you change whatever I had there to f of x equals k? And then just notice, just to kind of get this idea, does my curve f of x cross or touch y equals k? In this graph, it happens to do it 1, 2, 3 times. Well, that's just to get you, it's not that 3 is special, it's just to get you used to this idea of, does my function ever cross that horizontal line? Those are the kinds of places we're looking for. And if that point on my function and that point on my function are known, and I'm going to connect them with a continuous curve, if k is in between the two y values for those 2 points, there's no way to skip over k with a continuous function. So my curve will cross y equals k at least once. That's what the intermediate value theorem promises us. Let's try this example. Okay. If f of x is continuous and f of -1 is 2 and f of 5 is 4, explain why there must be a place, an x value, c, that has the output value 3. So f of c equals 3. So if you're going to compare this to the words in the original intermediate value theorem, let's see if we can figure out, what do you think is standing in for A? What do you think is standing in for B? And what do you think is standing in for K? Well, A is the leftmost x value. So I have two x values here, -1 and +5. So I'm going to say A is -1. B is +5. K is the output value, the y value that I care about. It's the y value that I care about, so K here is 3. So I'm going to strongly recommend at the beginning of your study of the intermediate value theorem, you try to make a picture every time, a graph, every time you use the intermediate value theorem. It's not technically required on the AP test, but I think to understand where some of these numbers come from, we want to understand this situation graphically. So I'm going to recommend plotting the two ordered pairs we've been given. I know f of -1 is 2. I think that's there. I know f of 5 is 4. 1, 2, 3, 4, 5, 1, 2, 3. And I'm going to strongly suggest that you think of k, think of the horizontal line, y equals k, and try to draw that in. So I know my k equals 3, which is 1, 2. That's y equals 3. So if I think about it, this question is asking me to explain why there must be some place in between, on the interval, -1 to 5, x goes between -1 and 5, where the y value is 3. Well, if I hadn't been told the function is continuous, I can't guarantee it. But I know continuous functions have no skips or gaps. So there is no way to connect those two blue dots without crossing the red line. So once I've decided that, and once I've identified sort of like my key player numbers, I'm going to use what I remember about using theorems to justify my work. And I'm going to write up my conclusion. So I'm going to type it out because it's definitely going to require words. I strongly suggest you try to get this exactly into your notes. So I'm going to sort of talk as I type here. I'm only guaranteed to cross that red horizontal line because, number one, I've been promised that f of x is continuous. So that has to be part of my justification. I have to promise that I actually stopped and considered, you know, that I can only guarantee that the intermediate value theorem works on continuous functions. So I check against my, I check against my problem statement and I read f of x is a continuous function. So I say, okay, since f of x is continuous on the x interval that I care about, on a comma b, or between a and b, and there's a second thing I have to prove that I thought about, and that's I'm only going to cross that red line when I connect my two blue points because I have one blue point that's above and one blue point that's below. So I have to confirm that I checked that I have one y value that's higher than k, in this case 3, and one y value that's lower. So this is the next part I would write up. So this is me writing it up in symbols. You could write it up in words, but it's less elegant. So one way to say I know one y is above and one y is below is to tell me what the two y values are. So f of -1 is 2. So that's the y value that's less than the y value I care about. I'm just going to notice here these should match. Sorry. Those should match, right? And these should match. And where does the 3 come from? 3 is the y value that I care about. So notice that my 3 here should match my k. So since I've checked that all the hypotheses are true, then I can conclude. I'm going to write up the rest. So here's the last part. Since f of x is continuous on the interval -1 to 5, and f of -1 is 2, which is less than 3, and f of 5 is equal to 4, which is greater than 3, so since my function is continuous and I have one point on either side of the y value I care about, therefore the IVT, you can write that, guarantees that there exists C. Notice I'm using the same letter they used. Between -1 and 5, between the two x values that I know about, for which f of c equals the y value that I care about. So you need all three parts for a complete write-up, a complete justification of an existence using the intermediate value theorem. You could give the parts in a different order, but we need all three parts. Please get this exactly into your notes and watch for connections between the words we used here and the numbers we used here and the words and numbers we use in the next problem. See if you can cement in your mind where each of these values, each of these letters came from.